who's tell me first? Yes, sir. Please tell me your name from boys side. Hello. Okay, is there CR is present or it not? Okay, I will keep it in presentation mode. Okay, I have kept in presentation mode. Is it visible?
Yes, sir.
Yes, sir.
Okay, fine. Okay, how many students are participate in this today's lecture? Can anyone tell me count?
53, sir.
53. Okay, we will wait for 3 minutes only. After we will start the session. We will wait for 3 minutes. Okay, can we start? Students, can we start?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. A very good morning, all of you. Today is our third lecture of DEM subject. Today's lecture it is addressed by Sawant sir. Actually, he has some unavoidable conditions, so that he yesterday told me, sir, can you conduct? Yes, I am on the lecture. So, very good morning, all of you. So, friends, yesterday lecture we were completed the big gates, universal gates. Thereafter, we know that it's a Boolean equation table. Thereafter, we see the special purpose gate. Thereafter, now we were looking for the ICs. Yesterday also we have covered the ICs. The IC 7400 is the NAND, 7404 is the NOT. Thereafter IC 7432 is the OR. IC 7048 is the AND gate. So yesterday only I have explained you all. This is just brush up for you all. So I hope all of you remember these the IC numbers. Now I am going to next slide. I hope all of you visible the next slide. IC's gate IC7404 is the NOR, IC7486 is the XOR, IC74266 is the XNOR. Right, these are the ICs, all are 14 pins. We know that there are two pins are the common, that is 14 number pin, it is always act as an VCC, and pin number 7 it is always act as an ground. So we never forgot this, right? Then after according to input and outputs of gate, we will very carefully look out the pins with associated with that gate. Okay, I'm going to next slide. I'm going to switch next slide. I hope all of you visible. Please, Sia, unmute your mic and tell me is it visible or not.
Yes.
Okay, I hope all of you visible the next slide, De Morgan's theorem. So yesterday only we are see the last point. This is the De Morgan's theorem. De Morgan's, it has the two theorem. One is the product of sum of two or more variable is equal to the product of complement of that variable. That is the first equation, which says that the first equation which says that a plus b bar is equal to a bar into b bar, a bar into b bar, right? So this is the De Morgan's first theorem, and also I have given you the homework. The homework is that we have to prove by using table. I hope all of you done this homework. That is the a plus b bar is equal to a bar into b bar. This is the De Morgan's first theorem. De Morgan's second theorem, the complement, the product of complement of variable is equal to the sum of the complement. That is a into b bar is equal to a into b bar is equal to a bar into, sorry, a into b bar is equal to a bar plus b bar. This is the second. A into b bar is equal to a bar plus b bar, right? The complement of product of two or more variable is equal to the sum of complement of that variable, right? Then after the, these are the two theorems of De Morgan's. Now friends, now where we use the De Morgan's theorem? While we are implementing the Boolean equation, while we are simplify the Boolean equation, sometimes we require to modify the circuit. See, all of you listen very carefully. While we are simplifying the Boolean equation, while we are implemented the actual equation into the gate diagram, so at that time we were minimize the equation. Why we minimize the equation? So that we will get the propagation time, it should be minimum. What is the propagation time? Propagation time is nothing but how much time particular gate or particular circuit or particular electronics device it will take after applying the input. All of you getting my point what I told you? See how I De Morgan's theorem, it is correlated. De Morgan's theorem, it is used for simplification of Boolean equation. So what is the necessity to simplification of Boolean equation? Suppose, suppose I will write here one equation. Suppose I will write here one equation. It is y equal to a. Suppose this is a into b, y equal to a into b plus a. Sorry, because of, okay, suppose the one equation y equal to a into b plus b into c. This is the first equation, right? And second equation y equal to a into b. See, I have told you two equation. One equation is y equal to a into b plus b into c. It has three variables, and in the equation it has contained the two terms. Right? First term is a into b plus second is b into c. Means in that equation it has contained three variable a, b, c. Right? And the second equation y equal to a into b, it has only two variable, right? So once when I implement these equation into the circuit diagram, when I implement these equation into the gate diagram, so at that time the simplification equation, the equation how much it should be minimum, that much it gives the quick response. Quick response means what? Once I apply the input, immediately I will get the output, right? It is called as the propagation time. So for that purpose we will implement all these Boolean equation and that case, right? Simplification of Boolean equation we will use. I switch to the next slide. Yeah, this is very important concept. This is very important concept. Why NAND, why NAND and NOR, these two gates are called universal gate. Why NAND and NOR are called universal gate? Can anyone guess why it is called as the universal gate? Why it is called as the universal gate? Yeah, I'm sorry, I forgot to make the changes in the spelling here. Universal gate. Fine. See, NAND and NOR gate are called universal gate because by using these two universal gate, we can implement any logic equation. By using these two Boolean equation, we can implement any Boolean function. All of you getting my point? What I told you? A gate that can be used to create any logic gate is called universal gate. Hence, NAND and NOR are called universal gates. Any Boolean function can be created using AND or AND NOT gate, right? AND or AND NOT gate can be implemented using NAND and NOR gate. Hence, NAND and NOR gate are called universal gate. So I repeat it once again. Any Boolean function, any Boolean equation, or any gates we can implement by using these two gates, that is NAND and NOR gate. Are you getting my point? Hence, NAND and NOR gate are called universal gate. See, if I give example of non-technical, suppose there are three logs, right? For these three logs, it has individually three keys. I give you a very non-technical example. Try to understand. There are three logs. For these three logs, it has individually three keys, right? That is, once I implemented such a case, single key, which it will unlock all these three logs. So that one key I called it is universal key. Are you getting my point? What I told you? येतं लक्षात सगळ्यांना काय सांगालो मी? Suppose तिथे एक तीन कुलूप आहेत. तीन कुलूपाचे सेपरेट सेपरेट तीन चावी असणार. बरोबर आहे. मी काय करतो, एक चावी असं असणार की जे तिन्ही कुलूप अनलॉक करतील. राईट. सो दॅट इंडिव्हिज्युअल की आय कॉल इट इज युनिव्हर्सल की. Same concept when I implemented in our gate, NAND and NOR gate, these two gates, by using these two gates we can implement basic gate, we can implement special purpose gate. By using these two gates we can implement any boolean function. So NAND and NOR are called universal gate. So all of you got this point? Can I switch to the next slide?
Yes, sir.
Okay, fine. I switch to the next slide. Is it visible?
Yes, sir.
Yes, sir.
Okay. Now see friends. Now I have told you NAND and NOR are called universal gate. Now this slide, this PPT, it shows the example of how NAND gate can be implemented all basic gates, right? Or I can also say that implementation of basic gate using NAND gate. So I request you all, please listen very carefully. NAND and NOR, these are universal gate, right? By using these two universal gate, we can implement any gate, we can implement any boolean function, right? Now I give the example. I'm implemented basic gate by using NAND gate. I'm implemented basic gate using NAND gate. Friends, now we have to remember the all boolean function of basic gate. So basic gates are not, create the pointer. See, the basic gates are not, and, and or. These three are basic gate. For not gate, it gives the A bar. For AND gate, it gives the A into B, and for OR gate, it gives the A plus B. See, this is the Boolean equation for NOT gate. This is the Boolean equation for AND gate, and this is the Boolean equation for OR gate. Right? Now I have to implement basic gate by using NAND gate only. Now look at this diagram very carefully. Now look at only this diagram very carefully. Now see, NAND gate, it has a true input. So what I do, I just short the second input to the first one. Second input to the first one. See, I have short, and I have assigned the only single input as a A. Single input as a A. Now we know the Boolean equation of NAND gate. It is A this side. It gives the one is A here and second A is here, right? So A into A, its complement. That is A into A complement. It gives the only A. A into A, it gives the only A. See, uh, some of the students, they are ask me some doubts. I never forget such a doubt. Sir, A into A, can we write A square complement? All of you getting my point? What I told. In last batch, one student asked, "Sir, here is A into A. So can we take A into A is the A square bar?" It's not actually multiplication. It gives the ending operation. Keep in mind. For our simplification, we say it is A into A. It is nothing meaning that it actually take the multiplication. Whether if both satisfied, then it will use the right condition at the output. Right. So here A into A and its a complement. Yes. Yes. Anyone want to talk? Hello. May I audible you all?
Yes, sir.
Okay. Here. A into A is the A bar, and this is the actually we have a laws. It is called as the commutative law, it is called as the associative law, distributive law. So these laws we have further in the next point. So before that, you keep in mind, it is A into A, it's a A bar, right? A complement into A complement is equal to A bar, right? So once I short the input, it gives the resultant A bar, which is the Boolean function of NOT gate, which is the Boolean function of NOT gate. Now here I complete the NAND gate as a NOT gate. So all of you got this, how I implement NAND gate is a NOT gate. Students, all of you got it. So it's a very basic how I implemented NOT gate using NAND gate. Yes or no? Hello, may I audible?
Yes, sir.
Yes, sir.
Students, I see whenever I ask you dot now, just please give me as much as earlier response, right? If you all are keep quiet, I am not. I am got something doubt whether you are understand or not, whether you listen or not, right? Please give me a fast quick response so that I will continue further, right? So here we complement NAND gate as a NOT gate. Now I implement. This is the second. This is the second. Here I implement NAND gate as a AND gate. Now look at the diagram. Can anyone me explain how I implemented this NAND as the AND? Yeah, please, if you know anyone, please unmute your mic and tell me. Otherwise, I will explain. Yes, how I implement NAND gate as a AND gate.
So here two NAND gates are connected,
Hmm?
uh, and in second NAND gate they are shorted.
Hmm?
Then second NAND gate become NOT gate.
Second
When
AND gate, right?
second NAND gate becomes NOT.
Yes, yes. Next,
Okay.
yes.
When we
Okay.
pass connection through AND B, uh, because of the NAND gate, it becomes AND gate. Reverse of NAND gate.
Right, right. Yeah.
That dot removes.
Yes, yes. Congratulations. Yes, you're absolutely correct. Now see here. Wait, now see here. Uh, here, this gate, this gate is similar to this gate, right? Means here the second NAND gate, it is act as an NOT gate. It is act as an NOT gate, right? It simply invert whatever it calls the input. And the first NAND gate, it has two input, one is A, second one is B, right? We know the Boolean equation. We got here A into B, its bar or its complement. Then I have shorted this output to this one. Now here you might be get confused, sir. I am applying the output of this NAND gate to the input of this. So I will get A into B bar upper side and A into B bar lower side. Hence I got the output A into B bar into A into B bar. No. That's not a logic. It is the logic of actually either 1 or 0. See, even if I return here a into b bar, but its value might be either 1 or 0, depends on the input condition. Depends on the input condition. Keep in mind, right? So once I got here either a 1 or 0, that 1 and 0, they appear same here. They appear same here, either 1 or 0, right? Then at this output we got the inversion of input. This is nothing but actual a into b. Why it is a into b? Because at the input side we are applying a into b bar, right? At the output side it gives the complement of input is a into b bar. Due to this second AND gate, it make again one more complement. It is the double bar means it is going to cancel, and we got only a into b. All of you getting it? So this is the a into b. That means we are implemented by using NAND gate. Implemented, this is AND gate. AND gate, right? Now the last one, how we can implement NAND gate as a OR gate. Now student, again I accept from you. Can anyone guess how it is implemented? Actually, I have given you entire diagram. Just you have to implement your own logic. Okay, for sake of our operation, I will assign the name. This is the first one, right? This is second, right? And this is your third one. This is your third one. Now tell me, what is the output of first NAND gate? What is the output of second NAND gate? And what is the output of third NAND gate? Yeah, please, any one of you sure if you answer? Or anyone if you want to guess, just unmute your mic and you talk. Yes? Yes? आन्सर सांगताना चुकलं तर चुकू दे बिनधास्त. कोणीही तुम्हाला इथे लगे फाशीची शिक्षा देत नाही. चुकलं तर चुकू दे बिनधास्त. सी वाय आय गिवन यू टाइम ॲट द टाइम ऑफ एक्झामिनेशन. आता समजा इथं कोणाचं तर लॉजिक चुकलं, आता मी ते लॉजिक करेक्ट करून सांगितलं ना, तुम्ही ते कायमचं लक्षात ठेवता. एक्झाममध्ये जर चुकून आलं तर एक्झाममध्ये तुम्ही लिहित असताना पण तुमच्या लक्षात येतं, अरे इथं सरांनी विचारलं ते पण माझं लॉजिक असं होतं, पण ॲक्च्युली करेक्ट लॉजिक असं आहे. सो दॅट आय हॅव गिवन यू टाइम, राईट? If anyone can guess, you can guess, otherwise I will explain. Yes? No one? Okay. Okay, I will explain. Now see, the first NAND gate, its input we are shorted and we assign the only one input as a A. Similarly, for the second NAND gate, we are shorted the both input and we assign the name as a B. Now these two NAND gate, now these two NAND gate, it act as an NOT gate, right? It act as an NOT gate. See, keep in mind, whenever for NAND gate we short both the input and assign the only one input, it act as an NAND gate, right? Here the same we are implemented here, right? We are implemented here. Here we are using two NOT gate, hence it complements the input. I got one is A bar and second one is B bar. Right? One is A bar and second one is B bar. Now these two complements of input we are applying to third NAND gate. Third NAND gate. So what is the input for third NAND gate? It is A complement. Second one is B complement. Now if you apply the A complement and B complement as an input, I got the output. It is combination of multiplication of A into B and its complement as it is, and due to this NOR gate, so reduce this NAND gate, we got the second complement. Right? See, I removed all the pencil marks and I told you this final. Now look at this equation. See, this is the output where I got the output of third NAND gate. Right? It's A bar into B bar and its total complement. Now friends, tell me how it comes. A bar into B bar, its total complement is nothing but A plus B bar. Sorry, A plus B.
Sir, by applying De Morgan's theorem.
De Morgan's which theorem? De Morgan's second theorem. Right? So once we apply De Morgan's second theorem, according to De Morgan's second theorem, the product of complement of variable is equal to sum of complement of variable. Right? Now here friends, suppose this A bar I have considered as a x. A bar I have considered as a x. B bar I have considered as a y. Suppose consider B bar as a y. Now its complement. Keep in mind this equation I have illustrated like this. That is here A bar it acts as an x, B bar it acts as an y and its complement. So according to De Morgan's second theorem, the x into y and its complement is nothing but x bar plus y bar, x bar plus y bar. Right? This is the xy plus y bar. Friends, once I know the value of x bar plus y bar, just simply put what is x? X is nothing but a bar. So we here got a its double bar. Right? We got here a its double bar. So I can replace it is simply by a. Once it is a double bar means it is cancelled. It gives the original value as a only. Right? Similarly, I got here y bar that is nothing but b double bar. It gives the only b, that is a plus b. All of you getting my point?
Yes, sir.
Now in this way we are convert the NAND gate as a basic gate. Right? So NAND gate I have converted as a NOT. NAND gate I have converted as a and NAND gate I have converted as a OR. This is the first step where I show how the NAND gate it is called as the universal gate. Now I will give the task for you. Implement implement NOR gate as a NOT gate, NOR gate as a AND gate, and NOR gate as a OR gate. Right? Now tell me how we can implement NOR gate as a NOT gate. Can anyone guess how we can implement NOR gate as a NOT gate? So what is the Boolean equation for NOR gate? What is the Boolean equation for NOR gate? Don't know?
Y equals to A plus B complement.
Y equal to A
A
plus
plus
B. Right, it's correct. Y equal to A plus B complement. Now I want to get a not get as only A bar. Right? Can anyone guess how we can implement it? Here, the output of NOR gate, we get A plus B bar. Now I have to convert this is only A bar. Yes. अरे why you are taking time? It's very simple. कसं करू शकतो? NOR गेटला दोन इनपुट असतात. One is A, second one is B. So the output we got A plus B bar. A plus B total bar. Right? A plus B total B bar. आता मला कसं करणार? How we can implement by using this gate? Implement not gate. कसं करणार? Now see here the input is A.
Take both output as a
Both. Yes. हाँ दोन्ही काय करणार आहे ना?
both input as a
Right.
both
Dot
Both
input
correct.
as
both input as A. What we get the output? Y equal to Y equal
a
to
plus a bar.
हाँ we got here A, right? A plus A plus A,
A bar.
right? A plus A and wait, A plus A and its total bar. But this is the not get. What I got not get. It should be only A bar. It should be only A bar. हे कसं मिळतं मग इथे तर A plus A bar आहे. कसं मिळणार मग आपल्याला फक्त A bar?
De Morgan's first.
डी मॉर्गनन्स फर्स्ट थेरम. बरं ठीक आहे. डी मॉर्गनन्स फर्स्ट थेरम काय म्हणताय? सी द प्रोडक्ट ऑफ कॉम्प्लिमेंट ऑफ sorry the sum of complement of variable is equal to product of complement of variable, right? Now here I got a bar into a bar, right? A bar into a bar is equal to, can I return this is the a bar? असं लिहू शकतो का मी?
Yes, sir.
Can we write this? Can we write this is the a bar? A bar into,
Yes.
yeah, that is the conversion of NOR gate. We are implemented. It's a basic first basic gate is a NOT gate. कळलं सगळ्यांना? आता ह्याच्यामध्ये तुम्ही एक लक्षात ठेवायचं, ज्या वेळेस नॅन्ड गेटचे दोन्ही इनपुट आपण शॉर्ट करतो, when we short both inputs of NAND gate it gives the NOT. Similarly, when I short both input of NOR gate it acts as an NOT gate. All of you getting my point? इथे लक्षात सगळ्यांना, ज्या वेळेस नॅन्ड गेटचे दोन्ही इनपुट आपण शॉर्ट करतो देन वी ऍक्ट ॲज अन नॉट गेट. सिमिलरली वेन आय शॉर्ट बोथ इनपुट्स ऑफ नॉर गेट इट गिव्स द नॉट, राईट? दिस इज द फंक्शन when we are implemented NOR as a NOT. आता मला सांगा how we can apply AND gate by using NOR. किती गेट लागतील आपल्याला नॉरचे अँड गेट इम्प्लिमेंट करायला?
तीन तीन लागणार.
करेक्ट, ऍब्सोल्युटली करेक्ट. 3 लागणार. फर्स्ट कशासाठी लागणार सांगा?
फर्स्ट ए बार साठी.
That is NOT gate. एक A bar, second B bar, output of A bar and B bar is connected to the third NOT gate, and we are applying De Morgan's first theorem. Right? Right.
Yes.
Okay. Okay, fine. And now tell me how we can implement OR gate by using NOR. How many gates are required?
Two.
Two.
Two gates, sir.
करेक्ट. कसं सांगा? 2. पहिल्या गेटचं आउटपुट असणार तुमचं, पहिला नॉट गेटचं आउटपुट असणार आहे ए प्लस बी बार. हा, सी द फर्स्ट नॉर गेट वी गॉट ए प्लस बी बार. सेम परत तुम्ही ते सेकंडला इनपुट म्हणून देणार. सेकंडचं आउटपुट काय येणार? ए प्लस बी, इट्स अ डबल बार. येतं लक्षात? ए प्लस बी, इट्स अ डबल बार, so that we got a plus b. All of you getting my point? लक्षात येतं मी काय सांगालो?
Yes, sir.
Okay, friends, see, even if I implement these all basic gates using NAND gate only, now you will come to know how to implement these basic gates by using NOR gate, right? Hence, for this purpose, we called as NAND. Hello, may I audible?
Yes, sir.
Yes, sir.
Okay. Now see, by using NAND and NOR gate, we are implemented all basic gates. For this purpose, NAND and NOR gate are called universal gate. Okay, I hope you all of you understand this point. Can I move to next slide?
Yes, sir.
Yes, sir.
Okay. I hope all of you looking the next slide.
Yes, sir.
Yes, sir.
Okay. Now see, this is the very important. Now we start number system. Now we start the number system. See, before we looking the number system, first I explain you what is importance of number system. Suppose friends, we all have a laptop, we all have a mobiles. In that, if you open the calculator, when I press 2 plus 2, when I press on the equal to button, I got the 4. Right? When I press 2 into 2, when I press equal to button, it goes the 4. Now we know that we assign the input to the calculator function, it produces the output as if we are which functions we required. But friends, what happened inside the machine? What happened inside the processor? Now check out, if I press the 2, so what understand by the processor? Right, whenever I press the 2, that means I give the processor the command which convert into the machine number or which converts into the machine language. Got my point? So even if on the screen it will display the 2, but it is not actually 2, it is not actually 2, that 2 it is by produced by the machine number. What is my point? So once I press the 2, again I press the plus sign, right? Again I press the 2. See, even if on the screen it will appear 2 plus 2 is equal to 4, but inside the processor it takes that its own number which it can perform the operation, right? Then after it process on it and it gives the result in the machine language number, and when the processor it want to display on the monitor, at that time only it takes the conversion and it gives the user defined or user readable number. येत्या लक्षात मी काय सांगालो सगळ्यांना?
Yes, sir.
See, even if I type, suppose I open the WordPad, I open the WordPad. In the WordPad, I have typed the few numbers. I have typed the something letter. We know that if I press the A, it displays the press A. When I press the B, it displays on the WordPad B. But friends, keep in mind inside the processor how the operation it goes in. It first encode the whatever you press the number, then after it process on it, then it decodes and again it display on the monitor, right? So that now we will understand how processor it do the arithmetic inside the processor. Right? All of you getting my point? आता इथं आपण काय बघणार आहे? We will check whenever if I assign 2 plus 2 is equal to 4. Right? But it is for the sake of our user, it is a 2 plus 2. We got the 4. But what happened inside the processor? How processor it performs arithmetic operation? So that we first learn the number system. Got it? Why we learn the number system? Students, may audible?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, can anyone tell me why we learn the number system from boys? Can anyone tell me why we learn the number system from boys? Yes, Usman Patel is there.
Yes, sir.
Yes, tell me why we learn the number system.
Sir, we have to know the what happens in the processor. If we
Yes,
take 2 plus 2,
yes, correct. Okay, right now I come to the conclusion. You all of you attend very carefully. Okay, friends, I am very happy. Now see, whenever we press, it's not only the 2 plus 2, if you do the something, any different operations also, how the processor it performs the task and what happen inside the processor, right? For that, we first learn the number system. In the number system, in the number system, in the number system, basically there are four types of number system. One is decimal, second is binary, third is octal, and fourth is hexadecimal. These are the four basic number system. Decimal number system have a base of 10. Decimal number system have a base of 10. Hence, it includes the total 10 number. Sorry, I just create the pointer. Now, the first is decimal number system. The decimal number system is a base of 10. Hence, it includes the 10 numbers and that 10 numbers are from 0 to 9. Right? 0 to 9 means it has a 10. Right? Hence, in the decimal number system, it has included the number 0 to 9. Second, the binary number system. The binary number system, this is the actually the processor number system where it has a base 2. It has a base 2 means it includes the only two number, that is one number is 0 and second number is 1. Keep in mind the decimal number base is a 10, hence it has a 10 numbers and that 10 numbers are start from 0 to 9. Getting my point? Second is the binary number system. Binary number system is a base of 2 and it has only two numbers. It is one number is 0 and second number is 1. This is for the binary number system. Third, it is the octal number system. Octal, it is a Greek word which is nothing but 8. Right? Octal, it has a base 8, hence it includes the total 8 numbers. and that numbers are start from 0 to 7. So here, if the number it is more than 7 number, it will not be included in the octal number, binary number. The number it is from 0 to 7, it is the octal number, right? Similarly, the hexadecimal number, it is short form, it is also called as hex number. So most of microprocessor they operates on the hex number. Hexadecimal numbers has a base of 16. So it has a base of a 16. It includes the total 16 numbers, right? So that it has a 16 numbers. The number start from 0. Hence, the 16 number last is 15. The number from 0 to 15, it is the hex number. But keep in mind, the number from 0 to 9, it is similar to like decimal number. It is similar like the decimal number. After 9, 10 to 15, they are assigned the codes from alphabets A to F. That means A is equal to 10, B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14, and F equal to 15. Friends, please note it down. I hope every time whenever the session is start, I hope you keep with your notebook and pens. Whenever I told you some important thing, you just note it down, right? So I repeat it once again. The hexadecimal number has a base of 16, right? Hence, base of 16, it includes total 16 number, and that 16 numbers are from 0 to 15. 0 to 15. In 0 to 15, the numbers from 0 to 9 are similar with the decimal number. The numbers are 0 to 9 are similar with the decimal number. The number 10, 11, 12, 13, 14, 15, they are assigned as a code. That codes are A is nothing but 10, B is nothing but 11, C is nothing but 12, D is nothing but 13, E is nothing but 14, and F is nothing but 15. So keep in mind, we always keep in mind A to F is nothing but it is a hex number starting from 10 to 15. Right. This is about the introduction part of the number system. We will check one by one. So you already got the basic number system. Is there any doubt
Yes.
here? Me? Okay, friends. Now we first check what is mean by a binary number system and how we convert the decimal number into binary. Friends, we know the decimal number we always use in our day-to-day life. So in day-to-day life, wherever we use the number, it is nothing but the basic decimal number, which is a base of 10, right? So I have a 5 mangoes, I have a 2 mangoes, that 5 to whatever we are saying, it has a weight is a 13 kg, 14 kg. These all numbers are decimal number. Now we know the binary number, which is a base of 2. Now I request you all, please note it down or please take the screenshot of this PPT first. How we convert the decimal to binary conversion. Now here I given the steps. The first I will read the steps. You look at carefully. Write down the decimal number. Divide the decimal number by 2. Write the result under near. Write the remainder on the right hand side. Divide the result of the division by 2 and again write down the remainder. Continue dividing and writing down the reminders until the result of the division is 0. Keep in mind until the result of the division is 0. Whenever we got the remainder is 0 or division is 0, we always return as divided by 2. So now check one example. Suppose now I want to convert 160 decimal number into binary. 160 decimal number into binary. Now see, now here onwards we always keep in mind whenever we define the numbers at that time we always write it's a base number outside the bracket. Now see, here it is a 160. Here we mandatory to write its base so that we will identify this is the decimal number, right? If we are not written the base, might be this number is octal also because the number it is less than 8, hence it is octal. So now here onwards every time we will write its base number so that we will know it is which type of number system. Now the first example, we have to convert the 160 decimal number into the binary number. Now see, I have written 160 here. I request you all please look out carefully. See, I written 160 here. Then after I divide by 2. So 160 divided by 2, I got the division is 80. I got the division is 80 and I got the remainder is 0. I written the remainder here, right? Again this remainder not is 0, it is 80, hence again I have divided by 2. Again I have divided by 2. Once I divide by 2, I got the division is 40 and its particular remainder is 0. I written the 0 here, right? Again I divide the 40, it's by 2. I got the division is 20, remainder is 0. Again I divide the 20 by 2, I got the division is 10 and here remainder is 0. Again I divide by 2 by 10, right? 10 divided by 2, I got the division is 5, remainder is 0. Now again I divide by 2 to the 5, I got the division is 2, here I got the remainder is 1. Right. Again once I got the 2, so I cannot make the division by 2, so I can write here 0 and division I got it is only 1, right? 2 divided by 2, I got the division is 1 and remainder is 0. Now here we cannot make the further division. See here we cannot make the 2, sir. Now I will do 1 divided by 2, I got the answer is 0.5, division is 0.5 and I write here it is like not like that, right? Keep in mind once we got the division is 1 till or until the division is 0, right? Still we will make the divider, but we never got once we got even if 1, we stop there. All of you getting my point?
Yes, sir.
Friends, all of you got my point?
Yes, sir.
How it comes?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Yes, sir.
Very simple, but the most important thing is that here the most important thing is that once I got the division successfully, right? Now see how I can write the binary number. How I can write the binary number. Now I don't forget we have to write the remainder. Now this direction shows it the upward. Upward direction means what? This is the MSB bit. This is the MSB bit. What is mean by MSB bit? It is the most significant bit, and this is the LSB bit, that is least significant bit. This is the least significant bit, that is MSB bit. We write always at left position, that means the 0, 1, then after 1 2 3 4 5, 5 zeros, right? 1 2 3 4 and 5. I'm sorry, I don't have right no proper practice to write this number by using the pointer, but friends try to understand. Sorry, I just make the all this erase my inside. so that come to know proper. So what is the final conversion? It is 0, right? 1, then after 5 zeros, that is 0, 0, 0, 3, 4, and it's 5, right? And once I complete the bracket, don't forget to write its base number as a 2, and this is nothing but our proper conversion of 160. 160, it is the decimal number. It is the decimal number, and its binary number it gives 0 1 0 0 0 0, right? This is the proper conversion of decimal number to binary. This is the proper conversion of decimal number to binary. Friends, don't forget to write whatever I show you image. I accept every time conversion. I accept the same things how I mentioned here. Don't forget to division by 2. Don't forget to write down the remainder. Don't forget to show this arrow. See, in the examination, a few students they forget to show this arrow. They forget to show this arrow. Friends, it will lose your marks. It will lose your marks. Keep in mind. So up till now, if you have query, you can ask. All of you got it? How I convert the decimal? Here this.
Yes, sir.
Okay. Any query for you all?
Yes, sir.
Please ask me. Any query? Please ask me. If you don't have any query, then we have only 5 minutes. I have give you some examples. You try to solve at your home, and I create one Google link. You can upload the all whatever task I have given you, right? Just I request you all of you, please note it down. Convert the following decimal number into binary. Please write it down.
Sir,
uh,
here MSB is 1, no?
Here this is
MSB.
ha this is the MSB bit, most significant bit, and this is the insignificant bit. Now, if we can say this is the MSB bit as a 0, still we doesn't get any problem on the result, because this 0 value stands for the higher number, right? So I will tell you how it see actually these shortcuts I will tell you. See, in your most of scientific calculator there are some function which gives the directly decimal to binary number, right? In that calculator if you use, you will got the MSB bit is 1. But friends, I have assigned the 0 for the MSB bit. It will not affect on the its value number, right? See why I assigned the 0 here, because I got the division is 1, and for this division I will not make the division by 2, and I will not write here as a reminder is write 0, 0 or 0. We cannot make the further process, right? So that I consider here a 0 as a MSB bit. Even if it is not affect on the value here, the MSB bit automatically it is 1. But in the answer we never forget to write down this 0 also. I will tell you, if we convert this number into decimal, it gives the only 160 value. It gives the only 160 value. Okay, please write down today's task. Convert the following decimal number into binary number. Convert the following decimal number into binary number. Write down first one. Write down first one 25 to the base 10. First number is 25 to the base 10. Second number is 96 to the base 10. 96 to the base 10. Third one, 284 to the base 10. 284 to the base 10. Fifth one, now write it down very carefully. Fifth one,
Sir, 4 to 1 na?
no, fifth one, na. First number is, please tell me, which is the first number?
25.
25. Second,
Second 96, sir.
first is the 24. Second is 96. Third one,
284.
284. Fourth one, 86. Fourth one, 86. Now, fifth one, write it down carefully. The fifth one number is 26.35 to the base 10. See, the fifth one is a fractional part. So, what is the fifth number? 26.35 to the base 10. See, I hope the fourth, up to fourth number, I'm sure you will solve very easily. But for the fractional part, intensely I have given you fractional part. See, even if it is not covered, just try it. Take, tell me what are the possibilities, sir, for fractional part, how we can convert, right? So, in the next lecture, first I will discuss with your homework. Then after we start with the next conversion. Okay, students, tell me, is there any fast? If you have any query, please ask me. I will solve your problem. Otherwise, we will stop here. Yes, any query?
No, sir.
No, sir.
No, sir.
So, with the permission, you all, can I stop here?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, friends. Thank you very much and wish you all the best. Please take care. Be safe at home. Chalo. So, with the permission, you all, I will stop here. Thank you.